Hello everybody, welcome back. We are moving into our next section where we're going to be talking about understanding virtual private networks and interfaces. And in this section, we're going to talk about things like Site-to-Site VPN Technologies. We're going to do a quick overview on IPsec VPN. We'll talk about Ike and its role, Internet Key Exchange. We're also going to talk about different IPsec modes. What are some of the other IPsec VPN types? We're going to get into a discussion and a discovery, a live demonstration and a discovery of Cisco IOS VTI. And then we'll wrap up this lesson here and we'll get into our wireless discussions. All right, we already have obviously talked about quite a few times what a VPN is, why a VPN is used potentially as a replacement to a classic service provider managed WAN, like a frame relay network or like point-to-point circuits or some other probably relatively costly and relatively static WAN type of environment, right? A VPN provides us the ability to scale our WAN topologies. It provides us the ability to add things like confidentiality, integrity, and availability in the fact that we're using the suite of protocols to provide that type of security in our environment, right? We can authenticate our peers. We can authenticate the devices that are functioning within the VPN, whether we choose to do some sort of pre-shared key authentication or certificate-based authentication. And so on. And we can even use these virtual private networks as an overlay, if you will, to a traditional internet-based connectivity, or an MPLS WAN. Now, not to suggest that MPLS is not a type of VPN. It certainly is. Frame relay, in fact, is even a type of VPN because those are virtually private networks. But when a lot of people think of a VPN, they tend to think of the concept of confidentiality through the form of encryption, message integrity through hashing algorithms and hashing methods and so on, anti-replay protection, all of the security processes that are provided by typically that IPsec protocol suite, which is really the focus of what we're going to be doing in this particular case. So this entire module describes the secure site-to-site connectivity options that we have. We are going to talk spend a lot of time talking about virtual private networking using virtual tunnel interfaces, Cisco IOS VTI point-to-point tunnels. In fact, we'll take a look at a discovery on that as well. All right. Now, when it comes to site-to-site VPN technologies, we do talk a lot about IPsec, but it's not really just about the protocols that we operate. It also happens to be the topology that we decide to implement. Certainly, IPsec as a general standard is a point-to-point VPN technology. It is point A to point B, and it doesn't really provide a whole lot of multi-point options. But there are many other types of VPN technologies that we can run that make use of the IPsec protocol suite that might allow us the ability to create this hub and spoke VPN environment where we have multiple spoke locations and we have a hub that allows us to interconnect, if you will, those spoke locations. Traditional Dmvpn, dynamic multi-point VPN, does that in fact. There are also other VPN technologies that provide us the ability to have multi-point connections where we can have a full mesh of connectivity. And because the WAN is not some sort of, service, well, it doesn't have to be anyway, some sort of service provider managed VPN or service provider managed network, the cost of doing things like a hub and spoke topology or the cost of even creating a full mesh goes down dramatically. And obviously, as we move from point to hub and spoke to full mesh, we see a lot of growth opportunity and redundancy opportunity and connectivity options that we have, right? So the topology itself is really defined by what types of interconnections we have between the different locations within the network. Interconnection is really just logical because the physical connections really just give us that access to the internet, give us that access to some sort of global transport, and then the VPN is created between those endpoints, simulating in essence that topology that we're seeing here. And you see logically the three different topologies that are used in site-to-site VPNs. An individual point-to-point connection. Point A is connected to point B using some sort of secure VPN path, which could include multiple point-to-point type connections, but that's also going to require mutual connectivity between those point-to-point locations. In the hub and spoke environment, we've got a centrally located hub, and then we have individual spokes, and then all of the spoke-to-spoke traffic typically would have to flow between from spoke A to spoke B or spoke A to spoke C through the hub, and then the hub can act as kind of that relay point, if you will, facilitating all of that spoke-to-spoke communication. In a full mesh environment, every device is connected to every other device in the network, and this allows any-to-any communication, but it also allows for redundancy, for path manipulation, and certainly for kind of a more efficient flow of information. All right, now there are some other types of topologies that you could have. You could have a partial mesh where maybe not every one of these locations is fully connected to every other location, but maybe Site A and Site B are your main primary locations. Site A is your corporate office in New York, and Site B is your corporate office in LA. And each of these additional sites out here would have essentially connections to those two main sites, and that would generate what we call a partial mesh environment. Now, it's a little bit less expensive, maybe a little bit less complicated to implement, but it still provides path optimization. It still provides that redundancy and scalability that we look for in a WAN design. All right. You could also have a tiered hub and spoke environment. So a network, if you will, of hub and spoke topologies where a device can act as a hub in maybe topology A and topology B, and it could act as a spoke in other topologies. So you might have, for example, this hub here, and then down here on this spoke router, it's acting as a hub for additional spokes that might exist in that region. This device right here might be acting as a spoke for devices that exist in that region, and so on. All right. Lastly, you could have something we call a joined hub and spoke environment, where basically it's just a combination of different technologies or different topologies, I should say. So maybe you've got this hub that has a point-to-point connection to Site A, but it's also got all these different point-to-point connections to these locations, and then Site A has a point-to-point connection to Site B, right? That would mean that we're extending essentially this hub and spoke environment from Site A over to Site B. And again, it's just really a matter of traffic flow, how you want your traffic to pass through the network. It's a matter of what types of transports you have, what your overall objective is for transporting the applications, and so on. All right, so that's something to consider in that design. All right, now look at the table here. We can see that we have different types of site-to-site VPNs. What are their objectives, as we would say, with regard to connectivity? Connected sites are connected together as a replacement to a classic private WAN, right? Which a classic private WAN in a lot of cases would require more cost, certainly more cost, and might require more stringent design requirements. For example, each site might have to have a specific service provider that it's connected to in order to facilitate the WAN. We might have to implement a specific technology that the service provider supports to allow those sites to communicate with each other. All right. We would also use some sort of peer authentication, and typically that could either be a pre-shared key authentication or we could use RSA-based authentication methods, which would involve the use of certificates and signed certificates and certificate validation. And then we would also have some sort of cryptographic path protection. That cryptographic path protection is really important, right? We want to ensure confidentiality, and typically this is done with the advanced encryption standard, where we're using AES either 128 or AES 256 to cryptographically secure the data flow, that symmetric data flow that occurs between the locations. I should say symmetric algorithm. AES is a symmetric encryption algorithm, meaning that we use the same key to encrypt as we do to decrypt, which would then protect the overall path. All right. We also want to be able to have some sort of network traffic control, what goes over the VPN, what doesn't go over the VPN. We can do this typically with some sort of crypto ACL, which allows us to define the interesting traffic that's supposed to pass over the VPN. Anything that doesn't fall within that would be considered, well, in essence, uninteresting traffic, and it wouldn't flow over the VPN. We also would want to use IPsec for its cryptographic services. We kind of talked about that in relation to cryptographic path protection. However, IPsec is a suite of protocols that provides us protection mechanisms outside of just confidentiality. There's a message integrity component with using MD5 or a SHA, secure hashing algorithm. There is an authentication component using RSA or DSA or pre-shared keys. There is a anti-replay protection component, making sure that somebody doesn't capture encrypted packets and replay them so that they could participate in the VPN. Making sure that there's some sort of key negotiation process. Typically, it's going to be Diffie-Hellman, and so on. So there's a bunch of different layers, if you will, to IPsec that provide all of these cryptographic features, and we want to make sure that we implement that. And when we look at our discovery, we're actually going to go through that process and implement each of those elements. All right. It says here, often work over controlled networks or like MPLS or internet backbones. Well, certainly you're going to have some sort of transport. And you might say, well, wait a minute, MPLS is a VPN. Why would I decide to implement IPsec on top of that? Well, it would be the same as saying, well, Dmvpn is a VPN technology that we would use over public domain internet routing. But in either case, authentication, encryption, message integrity, those mechanisms that IPsec provides are not built in to those designs. Well, certainly it's built into Dmvpn, but it's an add-on feature of Dmvpn that allows us to add those IPsec elements. MPLS natively doesn't have IPsec as part of its deployment. So we would probably add these IPsec components to make sure that we are providing those additional levels of security. All right. Certainly we want to always consider high availability, right? When we talk about security in general, we always talk about the CIA triad, the confidentiality, integrity, and availability triad. Certainly confidentiality, integrity, those are going to be taken care of by the individual protocols within ESP or authentication. But availability is really important as well. So we might have redundant termination points for our VPNs. We might have failover. We might have traffic engineering that we implement, and so on. And certainly we still want to guarantee that some of those other applications that require prioritization and so on are prioritized. So QoS, quality of service, would be something that we would implement as well. All right. There are many, many different VPN types that exist. And those would include things like Cisco EasyVPN or EasyVPN, GRE over IPsec, dynamic multi-point VPN technologies, virtual tunnel interfaces, group encrypted transport VPNs, what we call GetVPN. So again, there's just different types of VPNs that exist. All right. But the idea here is that we are using that IPsec or Internet Protocol Security protocol suite to secure our IP communication. We're adding authentication, we're adding encryption so that each IP packet in that communication session is sent securely. All right. We also have within the IPsec protocol suite protocols for establishing mutual authentication between the agents at the beginning of the session and the negotiation of encryption keys to be used during the session. All right. So IPsec overall is an end-to-end security scheme. It operates at the IP layer in the IP protocol suite, and it can be used to protect data flows between networks, between gateways, between hosts, even between a gateway and a host. All right. Now, we focus most of our attention in this discussion on the concept of site-to-site VPNs, but we also have the ability to run remote access VPNs as well, so that remote users can access their resources over some sort of public domain or shared infrastructure. All right. In Cisco EasyVPN, I mentioned that the Cisco router uses an SDM, what we call Security Device Manager, to use kind of an easy-to-use internet browser-based. SDM is kind of a browser-based management tool to configure the feature, right? In Cisco EasyVPN, we integrate VPN remote devices in a single deployment with a consistent policy and a consistent key management method. The idea, and that's why it gets this name, is that it simplifies remote site administration. All right, so we have our EasyVPN remote device to act as a remote client. We have our EasyVPN server to act as our VPN head-end device. We don't get into that too much in this section here. Actually, not really at all. But it is a different type of VPN technology. GRE over IPsec. IPsec does provide a secure method for tunneling data across an IP network, but as a protocol, it actually has quite a few limitations. IPsec doesn't support broadcasting or multicasting, which means that we're not able to use protocols that rely on those features like routing protocols. So it also doesn't support the use of multi-protocol traffic. It literally can support the transport of IP, and that's it. So if we add GRE, we talked about that in one of our previous sections, generic route encapsulation can be added to carry other passenger protocols like broadcast traffic, like multicast traffic, like non-IP protocol traffic. All right, so we can use GRE tunnels in conjunction with IPsec to give us the ability to run a routing protocol over that VPN, to run IP multicast or a multi-line protocol or multi-protocol traffic between the different offices. All right. So with this point-to-point GRE over IPsec solution, all the traffic between the sites get encapsulated in a point-to-point GRE packet before the encryption process takes place. As we talked about in one of our previous lessons, GRE is protocol 47, IP protocol 47. Dmvpn, dynamic multi-point VPN, that's a Cisco iOS-based solution for building scalable, and that's really important in this case, IPsec VPNs, right? It allows things like branch locations to communicate directly with each other in Dmvpn Phase 2 and Phase 3, talking about spoke-to-spoke communication. So if I have a voice over IP environment and I'm trying to communicate between branch offices, I don't have to have a permanent connection between those sites. I can use the spoke-to-spoke connection, which is, I believe, a temporary 2-hour connection if you leave everything to its defaults. As long as traffic is flowing, it's going to stay active. But it also enables Dmvpn zero-touch provisioning. We have zero-touch deployment of the VPN because we don't really care what the addressing of the spoke devices are, and the spokes automatically configure themselves to the hub and so on. All right. Now, VTIs, that's something that we're going to talk about in a lot more detail in this section here. A virtual tunnel interface gives us a routable interface for terminating IPsec tunnels It's really an easy way for us to define protection between sites to form this VPN overlay network. Those IPsec VTIs simplify the configuration of IPsec for the protection of the remote links. It's going to support things like multicast, and it's going to simplify network management. It's going to simplify network load balancing and those types of features. All right, the dynamic VTIs really function like any other type of real interface. So you can apply things like quality of service, firewall services, other security features as well, and those get applied as soon as the tunnel becomes active. The group encrypted transport VPN, they don't really mention it in the document here, but that's another very popular type of VPN technology. It is a Cisco iOS option as well. It's what we call a tunnelless VPN technology. It provides end-to-end security for network traffic in a native mode, but it allows us to maintain that fully meshed topology. So it uses the network's core ability to route and replicate packets between the different sites within the enterprise. It preserves all of the original source and destination IP address information in the header of the actual encrypted packet, so that allows us to do that native routing. All right, so it's very, very suitable GetVPN for MPLS, core networks, and it's also very suitable to encrypt things like multicast traffic. All right, so we're going to get into this in a little bit more detail. We need to learn a little bit more about the IPsec protocol suite, which we're going to spend some time on. But let's go through this question here. Which of the following solution enables site-to-site VPNs without a permanent VPN connection between the sites and then can dynamically create our IPsec tunnels? Well, that would be, ASA VPN doesn't really apply, right? ASA is Cisco's adaptive security appliance. That is not a type of VPN. Map Vpn also doesn't really apply here. Map is how we would potentially configure a VPN. So it's either between Flex VPN and Dmvpn. All right. Now, Dmvpn, it depends on how you look at it, right? Certainly with Dmvpn, we have the ability to do site-to-site if it's spoke-to-spoke without permanent VPN connections between the sites. But I don't think that's what they're referring to in this particular case, right? I mean, it could be, it's hard to interpret what they're asking here. I mean, certainly with the spoke-to-spoke communication, we have the ability to create those temporary VPN tunnels. We always will have a permanent VPN tunnel to the hub, if you will. But let's talk a little bit about Flex VPN. I didn't really mention that. It says here another solution, Flex VPN, uses the capabilities of IKEv2. VPNs have been around forever, right? They're a classic resource designed to securely and inexpensively extend the reach of our corporate networks, if you will. All right, and as I mentioned already, there are many, many different options available that are built on top of IPsec, which is our framework that deals with the issues of ensuring things like confidentiality, like integrity, like authentication, and even key management and key distribution. Now, there are some certainly basic strengths of IPsec, right? It's independent of transport because it does operate at the network layer. It doesn't care about UDP or TCP or even if it's just raw IP. The provisioning is easy, and as I swap out components or I swap out configuration elements like hashing functions or cryptographic elements or cryptographic functions, I should say, that's easy as well. So we can keep up with the hardware evolution, if you will, in terms of work factor and what's recommended as a security standard in a lot of different cases, right? If you're familiar with Cisco iOS software, you've heard of classic IPsec VPN. You've probably heard of GRE. You've probably even heard of a virtual tunnel interface. You may or may not have heard of EasyVPN, but you've certainly probably heard of Dmvpn. All right? But I guess the question is, which of those options should I actually select? All right? Each of those particular options were developed to solve specific problems, right? Crypto maps. These are kind of the initial legacy solutions, if you will. They mentioned Crypto Map VPN at the bottom there. This was actually derived before IPsec or even before an RFC, all right? The services available with crypto maps are really, really basic, but they do help if I have interoperability problems or compatibility options, or compatibility issues, I should say, between different devices. A VTI, that takes that logical interface into IPsec deployments without the need of using something like GRE. EasyVPN allows your branch routers or VPN appliances to behave like hardware clients to a centrally managed and centrally controlled VPN. Dmvpn provides the capability of dynamically establishing tunnels between spokes. So I really think in this particular case that would be the appropriate answer for this particular question. But still, I wanted to get into this idea of Flex VPN, all right? Cisco offers kind of what we would define as a unified way of dealing with all of these different VPN options. It allows the network to be prepared to simultaneously handle different VPN models, right? And that's what Flex VPN is all about. It's a flexible option for configuring VPNs. A router that's implementing Flex VPN could be configured to expect connections from different forms of VPNs: VTI, EasyVPN, GRE over IPsec, or IPsec over GRE, whatever. Dmvpn, classic IPsec, and so on. So it can deal with things like remote access. It can deal with site-to-site VPNs. It supports V4 and V6. Authentication and authorization can be performed by using a local database with Radius, and so on. The critical point where Flex VPN does not allow flexibility, though, is for the security association negotiation and establishment. We'll talk about that in more detail a little bit later on. Flex VPN requires that you use version 2 of the Internet Key Exchange Protocol, or IKEv2, which is really just a more secure option than the original IKEv1. All right? Certainly IKEv2 and the configuration of IKEv2 is a lot different, but in essence, that is the, and we'll talk more about Ike and its role in VPN establishments later on in this section, but that is certainly something that you would have to consider with Flex VPN, is that you don't have the ability to run IKEv1. So your platforms are going to have to support IKEv2. All right, so we'll go with Dmvpn in this case because I really honestly think that makes the most sense based on the wording of the question, because Flex VPN doesn't really deal with that aspect of it. All right. All right, so now let's talk a little bit about IPsec overall, right? IPsec is, in essence, it's an IETF standard. That's the Internet Engineering Task Force standard. And it's a suite of protocols between two communication points across an IP network that provides things like authentication, integrity, confidentiality. It's going to define encrypted and decrypted authenticated packets, and it's basically the protocol needed to secure key exchange and key management within it as well, right? We can see actually three major blocks here. IPsec, defined in RFC 4301, is a security architecture, and it offers things like encapsulated security payload. And ESP is or what we call encapsulating security payload. It is a transport layer security protocol, which is actually designed to function with both stacks, if you will, V4 and V6. It takes the form of a header that actually gets inserted after the IP header, but before the upper layer protocols like you might have with TCP, UDP, or ICMP, and before any of the other IPsec headers that have already been put in place. ESP gives you protection to the upper layer protocols with a signed area, right? And that signed area indicates where the protection data packets have been signed for things like integrity. It also provides for encryption, which indicates that the information is protected with confidentiality. So unless a data packet is being tunneled, ESP, and we'll talk about the difference between transport and tunneled mode, ESP only protects the IP data payload, not the IP header, right? That's why we have that ESP, all right? So ESP provides us things like confidentiality, authentication of data origin, connectionless integrity, and traffic level, I suppose, confidentiality with anti-replay services and so on. Anti-replay service is kind of a sequence integrity which guards against the use of credentials which were captured through man-in-the-middle attacks or sniffing attacks and so on. All right. Now the header itself is designed to provide a lot of different security services. And ESP could be applied in isolation by itself, or it could be applied in combination with Authentication Header. Now the Authentication Header, or what they document here as AH, is a security mechanism that allows us to authenticate the origin of the datagrams. It could either be the packets of the data transmitted through IP or different IP conditions and so on. And it is guaranteeing the integrity of the information that's being sent. Authentication Headers, part of IPsec protocol suite, doesn't provide encryption though, doesn't provide for confidentiality. So oftentimes you'll see AH and ESP being used together in conjunction to provide both the authentication process and the encapsulated security payload process, which is our encryption process. So it says here, IPsec is defined in RFC 4301. It combines the protocols of Ike and Ike v2, Authentication Header, and encapsulated security payload for a cohesive security framework. All right. So it is a suite of protocols. In fact, let me go ahead and pull up a diagram to describe what the different blocks are of this protocol suite. So if you look at IPsec as an overall architecture, as an overall framework of protocols, we can see the different building blocks here, right? I can run IPsec with authentication, which is going to provide authentication and integrity, but it doesn't provide any confidentiality, and certainly key exchange and key management would be critical to either version of IPsec. With ESP, I'm adding encryption. I'm adding the confidentiality piece. So it could be DES, it could be triple DES, could be AES, but I'm still going to have the integrity and authentication elements. DSA could be here as well. There are certainly multiple versions of SHA and so on. So when we keep talking about the overall framework, that's what I'm talking about in this particular case. We have kind of these pluggable modules, if you will, that allow us to define how IPsec is going to be implemented. All right, so that's what they say here. IPsec provides security services at the IP layer. All right, now specifically, IPsec itself is not the network layer protocol. It is a suite of protocols. And in fact, if you look at the list of protocols from the IANA, you'll see that ESP is protocol 51 and AH is protocol 50. All right. So it does run right on top of the IP layer, and it puts in place all of these features that we talk about, depending on how you decide to implement it. IPsec can protect different paths by adding these multiple layers of protection. All right, encryption, confidentiality, etc., etc., etc. All right. Now for the transport mode, these headers are placed in different locations depending on what the goal is of, and we'll talk about, before we wrap up this particular slide here, the difference between tunnel mode and transport mode. Now, one of the boxes I didn't talk about here is the Internet Key Exchange. It could either be Ike v1 or Ike v2. It just depends on the version, of course. But this is going to be the suite of protocols, or the set of protocols, or it is a protocol, I should say, that is used to set up the security associations within the IPsec protocol suite. Ike actually builds on the Oakley protocol and Icmp, Internet Security Association Key Management Protocol. And it's going to use things like X.509 certificates for authentication, or pre-shared authentication, or we can use DNSSEC for distributed authentication. And it's going to use things like the Diffie-Hellman key exchange to set up a shared secret key for the session, and that's how we cryptically derive and share our keys. It also does security policies for the peers to allow them to connect together. Now, it is an IETF standard, all right? That was originally defined, Ike was originally defined in the late 90s, I believe it was. RFC, 2407, I believe. Actually, there were multiples. I think 2407 was the first one. That was Icmp. 2408 and 2409 was actually the one that was used for Internet Key Exchange. Let me see if they mention that here. No, they don't mention it in the documentation here. But and then we had some additional RFCs that were released. Certainly 4306 to introduce Ike v2. That was in the early 2000s. All right. So you know, we'll get into the specifics of the protocol a little bit later on. What are the different phases? What did Ike v1 do versus Ike v2, and what kind of improvements did we have with Ike v2, and so on. All right, but it says here, Ike, the Internet Key Exchange, provides management of the keying material in IPsec. defines authentication, but without encryption. There is no encryption provided by And again, this is Protocol 51. An ESP encapsulating security payload provides that encryption. All right. We can use or ESP either independently or together. Most people will use ESP. by itself is certainly considered to be somewhat obsolete. In fact, it's not even really supported in a lot of different Cisco implementations. All right. So what is an IPsec security association? A security association, in essence, is the establishment of shared security attributes between two different endpoints to support whatever secure communications we need to support. It can include the attributes like what cryptographic algorithm am I going to use, what mode of cryptography am I going to use, what are the keys that we're using for the cryptographic process, what are the parameters for the data to actually be passed over that connection, right? It is essentially the framework for establishing the communication channel between the endpoints. And one of the key elements in this is what we call the Internet Security Association and Key Management Protocols, along with Ike, the Internet Key Exchange, and then there's some other ones as well. All right. Now, an SA is actually simplex. It's a one-way channel, even though it is established in both directions. Each device is responsible for establishing its own simplex security association logical connection, which provides that secure data connection between the devices. Now, typically, you do see them in both directions because ultimately, network data flow typically happens in two directions, right? I'm going to send you data, you're going to send me data back. But the fundamental requirement of an SA comes into play when two entities communicate over, say, more than one channel, right? So maybe you have a mobile subscriber and a base station. The subscriber could subscribe itself to different services within that environment, and then each service is going to have different service parameters, different data encryption algorithms, different keying material, different initialization vectors, and so on. So to make things easier, all of that security information gets grouped logically, and then that logical group itself becomes that security association, and so on. Each of these security associations are going to have their own ID. It's called an SAID, so that we know what profile we're using and so on. So in essence, an SA is really just a logical group of security parameters that enable the sharing of information to appear, okay? So it is a fundamental component of IPsec. Both AH and ESP are going to use security associations. And here, they're kind of breaking it down just what I said here, right? And this is really the main point of the section. A security association is a simple description of current traffic protection parameters. What algorithm am I using? What keys am I using? What are the traffic specifications? In other words, what is getting encrypted? What is not getting encrypted? And so on, all right? So we'll talk more about that as we start to do our implementations and we get into the different options for implementing our VPNs. We're only going to take a look at one, but it's going to have some of the core elements that other VPN solutions might have as well. All right. IPsec itself can actually be configured to operate in two different modes of operation. It can operate in tunnel mode or it can operate in transport mode. Each of those different modes will depend on whether you decide to use one versus the other will depend on the requirements and the implementation of IPsec itself. All right, now IPsec tunnel mode is the default mode of operation. And what I want to do is I want to pull up a diagram because I want to make sure that you can see this visually as we're going through the process of discussion. So here's the diagram, and with tunnel mode, the entire original IP packet gets protected by IPsec, and we can see that at the bottom here, right? We can see encryption is being applied to the original packet that was being transported. So basically, in this sense, IPsec wraps the entire original packet, it encrypts it, and then it adds this new IP header and sends it to the other side of the VPN. It is the most commonly used between type of connection between, say, a Cisco router and another Cisco router, or a Cisco router and an ASA, which we define essentially as our gateway, right? That's the gateway that's providing that cryptography. So tunnel mode is used to encrypt the traffic between those gateways. All right. Configuration and setup, we're going to go through kind of when we do our VTI implementation a little bit later on. All right. Another example of tunnel mode is an IPsec tunnel between, say, a VPN client and an ASA or router. The client connects to the gateway. Traffic from the client gets encrypted, encapsulated inside of a new IP packet, and gets sent to the other end. Once it gets there, it gets decrypted by the firewall appliance or the router with the firewall services, and then the client's original packet gets sent into the local network. All right. Now in tunnel mode, whether you're running AH or ESP, it's going to, that ESP header is going to be inserted between the IP header and the original IP header and the new ESP or AH header, in our case, ESP header, was what we're seeing depicted in the diagram here, which is going to be used for transporting the information. Now keep in mind that the protocol ID that is defined in this new IP header is protocol 50. Okay? If I was doing IPsec with AH, I would see right between here, the IP header, I would see an authentication header, and I would see my new IP header here, and the authentication piece would actually encompass everything. The new IP header, as well as the AH and then the rest of the data. All right. But again, it would not include any type of cryptographic protection of the payload information. We don't protect the data fields and we don't protect the information. Now in transport mode, that's typically going to be used for end-to-end communication. For example, communicating between a client and a server, like a workstation and a server, or a workstation and a gateway, if the gateway itself is basically acting as a host, maybe a telnet session or remote desktop session or something like that. Transport mode provides the protection of the data, our payload, and it consists of our, as you can see from the diagram here, a TCP header, our transport layer header, our data header, but the original packet header falls outside of the encrypted data, right? So the payload is encapsulated by IPsec, but not the original IP header. The original IP header remains intact, except in this particular case, the protocol field is changed to either 50 or 51, depending on whether we're using AH or ESP, and then the original protocol value is going to be saved in the IPsec trailer, and then that gets restored once the packet gets decrypted. All right, so again, transport mode is typically used when another tunneling protocol like GRE is used to encapsulate the data, and then IPsec is used to protect that encapsulated data. All right, so the packet, the diagram that we're seeing here kind of describes all of the, well, at least visually, what we just discussed. All right. So it says here, which of the following three protocols are combined in IPsec? ESP, AH, and Ike, right? SSL is a type of VPN as well as TLS, but it is not traditionally considered IPsec, and TCP is just a transport layer protocol. All right, so now let's get into some details about Ike, the Internet Key Exchange, right? Ike, again, either Ike v1 or Ike v2, and we talked about this in a little bit of detail on the previous slide, allows us to establish the security association between our peers. Now, the overall architecture of Ike is relatively straightforward, right? You can see here that Ike allows us to derive our Icmp, which we call our Internet Security Association Key Management Protocol, which allows us to define our Ike Policy, which includes things like authentication, encryption, the message authentication code, the group, the lifetime, and so on. So when we're setting up our IPsec peers, we have to agree on what this policy is going to be. What is the authentication method that we're going to use to authenticate the peers? How do we identify the peers? Is it going to be a pre-shared key authentication? Are we going to use RSA authentication? What is the encryption method that we're going to use? How are we going to protect the data and ensure confidentiality? The hashed message authentication code method to make sure that we can identify the sender, make sure the message maintains its integrity and isn't modified on its way to the destination. The Diffie-Hellman group to allow us to determine the strength of the encryption key itself, right? Diffie-Hellman group 2, group 5, group 7, etc. We'll get into this in a little bit more detail a little bit later on. All right, but we use all of these different algorithms and all these different elements of configuration to establish the security association, and that's what we talked about. We can also identify within Ike what is the lifetime of the security association, and that can be done based on the amount of data that passes back and forth between the clients or the amount of time that passes between the initial authentication. All right, Cisco IOS uses both the Icmp and the Ike keyword kind of interchangeably, so you might see it referenced a couple of different ways. Now, Ike uses UDP packets specifically on port 500, And it does require 4 to 6 packets with about 2 to 3 round trips to create this overall security association on both sides, right? The negotiated key material is then given to the IPsec stack. So we could use AES keys, information identifying the IP endpoints, the ports that are supposed to be protected, what type of IPsec tunnels getting created, and so on. In turn, the IPsec stack intercepts all of the relevant IP packets, and when it's appropriate, performs that encryption or decryption based on whatever the requirements are based on our policy. Implementations are going to vary on how that interception of packet is done. Some use virtual devices, some take a slice out of the firewall, if you will, and so on. Now, we do have 2 different versions, Ike v1 and Ike v2. Ike v1 consists of 2 different phases, phase 1 and phase 2. Now, Ike phase 1, the whole purpose of Ike phase 1 is to establish a secure authenticated communication channel using the Diffie-Hellman key exchange algorithm so that we can generate a shared secret key to do our further Ike communications and so on. All right, so we have this one, kind of negotiated, if you will, single bidirectional security association. Remember, that sounds a little bit confusing, right, when we say that, but again, these are simplex communication channels, but generally they are established in both directions. All right, now the authentication can be performed with regard to authenticating the peers. We can use pre-shared keys, which is what we refer to typically as simply shared secret. We can use signatures. We can use public key encryption, and so on. Now, I don't know if we'll get into this in as much detail later on, but there are actually 2 different modes that Ike v1 operates in, particularly phase 1. We have main mode and we have aggressive mode. Main mode protects the identity of the peers and the hash of the shared secret key itself by encrypting that information. Aggressive mode basically doesn't. All right, now in phase 2, the Ike peers use that secure channel that was established in phase 1 to negotiate the security associations on behalf of, say in this particular case, IPsec. And that ultimately results in 2 unidirectional security association streams, one that's outbound and one that's inbound. Ike phase 2 is only done in quick mode. Now, there were inherently problems with Ike, all right, which is why we talk about using Ike v2. Ike had a lot of different configuration options, but it actually didn't have a general facility for automatic negotiation of well-known default configurations that are typically going to be universally implemented. So both sides of Ike had to exactly agree on the type of security association that they wanted to create piece by piece, right? Step by step, or that connection could not be established. And then we had some other complications that also arose as well within the protocol. All right, so there were a lot of there's a lot of openness, if you will, to the interpretation of the implementation of Ike specifications. There were also some design faults. Dead peer detection was one of those elements. We don't have to get into the specifics, but the idea is that it just wasn't baked well enough, right? So Ike v2, which came out kind of the early 2000s, like I said, I think it was around 2004, 2005, RFC 4306, basically provided enhancements to things like NAT traversal, stream control transmission protocol, a very simple message exchange, fewer cryptographic mechanisms were built into it. It had additional reliability and state information that was included, and it had additional protection against things like denial of service attacks. All right. You know, I don't need to get into the, I guess, the specifics, if you will. That's kind of beyond the scope of this class. But it is certainly something that you would want to, you know, kind of take a look at later on down the line as you're getting more into the security components if you're doing a CCNP security or something like that. All right. Implementing Ike in your IPsec configuration can have several benefits. Ike can match multiple policies, which allows for a scalable configuration, meaning that you could have different policies that apply to different peers and so on. All right. Which of the following statements is correct concerning the configuration of IPsec peers and the Icmp policy? This Icmp policy should not include encryption method. It must be clear text. Well, obviously that's not going to apply. We don't do anything in the clear with regard to security. Icmp policy should include encryption, protect the data, and ensure privacy. Sounds about right, right? We definitely want to have confidentiality. The Icmp policy should include private keys to protect data and ensure privacy. No. Well, I mean, the keying material, the key string or the key variable, crypto variable, should definitely be secret, but I'm not sure that's what they're referencing in this particular case. This Icmp policy should include unlimited time so the encryption is not exhausted. No, we always want to have a lifetime for the data. We always want to specify that the data, that the encryption method that we're using or the encryption information that we're using is only good for a particular period of time. All right, so I would say B applies in this case. We definitely want an encryption method. We see that listed here as part of the policy, right? Defining the encryption method so that we can protect the data. All right. Now, this slide here, we kind of already did a deep dive into in one of our previous discussions, so we can just kind of skip over this. But again, transport mode encrypts only the data portion of the payload, each packet, and leaves the packet header untouched. We can see that listed up here. And then tunnel mode is more secure because it encrypts both the payload and the header. Gateway or host-based implementations, typically either encapsulated packets or host-to-host communication, and tunnel mode is typically used for gateway-to-host or gateway-to-gateway communication. All right, so we don't need to get into a lot of detail here. We've already kind of taken a look at this. Which two encryption modes does IPsec support? Well, obviously, tunnel mode or transport mode. All right. Now, with regard to the different types of VPNs, we also spent quite a bit of time talking about this as well. We talked about Dmvpn in general. We definitely spent some time talking about Flex VPN, and we're going to spend a lot of time talking about VTIs. In fact, the next couple of slides in our discovery is all about VTIs. Virtual Tunnel Interface allows us to configure our IPsec VPN, pretty much a site-to-site VPN, but it gives us a way to designate a path across the shared WAN, which pretty much every other VPN does with different packet headers, right? Meaning that we're kind of creating this tunnel mode transport, if you will. All right. We're going to see the details of IPsec VTIs coming up. And notice here it says it's a highly secure connectivity for site-to-site VPNs, which really kind of would apply to any VPN architecture, quite frankly, right? Every VPN architecture provides a secure method of site-to-site communication. But it says here with Cisco Avid. Now that term has been around for decades. It stands for the Architecture for Voice, Video, and Integrated Data. The Architecture for Voice, Video, and Integrated Data, meaning that VTI is suitable to support things like quality of service, traffic prioritization, and so on. Now, Dmvpn is a Cisco iOS-based solution that allows us to build a scalable IPsec VPN. And it provides a lot of flexibility. There's a lot of benefits to running a Dmvpn. All right, in a Cisco Dmvpn, we use a centralized architecture to allow us to provision and implement our VPN solution but it provides us the ability to have granular access controls and so on. You can see here that we have a central site that's going to act as our Dmvpn hub, and then we have our spoke sites. Now there are basically 3 different types of Dmvpn: phase 1, phase 2, and phase 3. The key differences between phase 1 and phase 2 and 3. Phase 2 and 3 allow for spoke-to-spoke communication. Phase 1 does not allow for spoke-to-spoke communication. So you all have a traditional hub and spoke design with phase 1. And then there are some slight differences between phase 2 and phase 3, and it has to do primarily with how the spoke-to-spoke tunnels are established, right? A Dmvpn phase 2, we need to use the redirect option from the central site. That would be phase 3, excuse me, the redirect option. In phase 2, we actually do a query, an NHRP query, and we get a reply from the hub to define how we can communicate to the other spokes. In phase 3, that's when we get the option of doing the NHRP redirect. And we don't need to get into the details. Certainly in some of our other courses, we get into a lot more detail into Dmvpn, but we don't have to get into it in a whole lot of detail here. I'll probably give you a little bit more information. We can see the benefits, right? Lower capital and operational expenses, simplified branch communication, meaning that we can allow that branch-to-branch communication if we are running Dmvpn phase 2 or phase 3. Really reduce deployment complexity, because at the hub, we don't have to define every single spoke independently. We create a generic multi-point GRE interface on the hub, and then the spokes will actually call home and they'll register to the hub to attach themselves to the Dmvpn environment. All right. So the Dmvpn architecture, again, I don't know that we need to get into it in a whole lot of detail, but the Dmvpn architecture does provide a lot of flexibility in communication. It is depending on how you implement it, it's a relatively simple configuration. We define the characteristics on the hub, which is basically kind of a generic multi-point GRE interface with NHRP and GRE and IPsec configurations. And then on each of the spokes, we just point them to the hub, right? The benefits of Dmvpn that makes it kind of more preferred over traditional IPsec VPNs is we get that full mesh connectivity option, right? We still have a basic hub and spoke configuration, but we have the full mesh capability in that we, in Dmvpn phase 2 and phase 3, we have the ability to do spoke-to-spoke communication. All right, we also have automatic IPsec that's triggered for building the IPsec tunnels. We don't necessarily have to set up different IPsec profiles and different IPsec cryptographic communication mechanisms, because IPsec is really just a switch that allows us to add that IP security on top of the Dmvpn network. All right. We have zero-touch deployment for adding remote sites, for example. It doesn't matter how many spoke sites you have. The Dmvpn hub configuration remains the same. And we have other benefits, right? Cost-saving benefits, etc. All right. Now, there are essentially 2 different deployment models that exist with the Dmvpn architecture. It can be deployed as a traditional hub and spoke deployment model, or it can be configured as a spoke-to-spoke deployment model. We use kind of the 80-20 rule. All right, 80-20 rule has been around for a long time, but that allows us to define what type of Dmvpn model we might use. If 80% or more of the traffic from the spokes are directed towards the hub, then we're going to stick with kind of a traditional hub and spoke model. If more than 20% of the traffic is meant for other spokes, then we start looking at the spoke-to-spoke model. Also, if you have a network with a lot of IP multicast traffic and so on, typically that's where the hub and spoke model is going to be preferred. All right, So there are some key elements to Dmvpn as well. Probably one of the most critical pieces to Dmvpn is the ability to run a multi-point GRE tunnel interface. That allows a single GRE interface to support multiple IPsec tunnels, which really simplifies the configuration completely. Because we can do traditional point-to-point IPsec with GRE and communicate between endpoints, and we can create a hub and spoke environment with that. But the hub configuration would be exponentially complex based on the number of spokes that I might have in that type of an environment. All right. The dynamic discovery of the IPsec tunnels and the endpoints and the crypto profiles, that's a really key component as well. It eliminates the need to configure static cryptographic mappings for every pair of IPsec peers, which really simplifies the configuration overall. And then, of course, the last major component is NHRP, the Next Hop Resolution Protocol. This is what allows the spokes to be deployed dynamically. We don't need to know what their public IP address is. The hub basically allows those spokes to register. The hub makes a database of registered spoke endpoints, and each spoke then registers itself to the hub with its real IP address, and then when it needs to communicate to other spokes or whatnot, it might do like an NHRP query for to the hub, to that database. That's typically what happens in Dmvpn Phase 2 to define the real IP address of the destination spoke. All right. So again, there's other benefits to Dmvpn. We talked about the zero-touch deployment, the spoke-to-spoke tunnels, dynamic addressing for spokes. It does work with NAT traversal. It supports IP multicast. It supports quality of service, high availability. We can have multiple hubs. It is VRF aware and VRF capable. And of course, it will work over MPLS as well. So again, lots of different options. And it's been around for a very long time. So it's been supported on multiple platforms for quite some time. Now, we did spend quite a bit of time in one of our previous slides talking about Flex VPN, and I kind of went through the details there, so I'm not going to spend a whole lot of time. But if you recall, it's kind of like it gives us the ability to commingle VPN solutions and VPN technologies as well as VPN architectures. Maybe I have Dmvpn and GetVPN and other types of VPNs that I'm using. Flex VPN gives us that capability. But like I said, one of the restrictions of Flex VPN, even though we don't really kind of consider it a restriction because Ike v2 is pretty much the preferred standard in this case, is that Flex VPN relies on Ike v2 for providing those that security in the configuration. All right. So Cisco IOS Flex VPN is a unified VPN solution, right? We can use public internet. We can use MPLS. Very easy to deploy. We have a single Flex VPN deployment, which supports all types of different types of VPNs. We can do failover redundancy. We have third-party compatibility because, again, we support multiple types of VPNs. It supports a multicast in QoS. It is also VRF aware, just like Dmvpn and so on. Very easy to control. Centralized policy control. We can create split tunneling policies to say, okay, this traffic goes over the VPN, this traffic doesn't go over the VPN. We can create our VRF selections, our DNS servers, pretty much all the things that you would typically associate to an IPsec VPN. It just provides more flexibility in this particular case. All right. Which VPN technology was created to cover all types of VPN? Well, we just talked about that. Flex VPN. Site-to-Site VPNs, remote access, teleworker, managed VPN services, and so on. Sorry about that. All right. So our next topic, and before we get into our discovery, is going to be discussing our VTIs, our virtual tunnel interface. This is a little bit of a longer discussion, also because we're going to be using our, actually using our discovery to take a look at how we configure a Cisco IOS VTI. Now, when it comes to IPsec with virtual tunnel interfaces, the benefit here is that it provides a routable interface for terminating our IPsec tunnel, and it gives us an easy way to define the protection between the sites to form our overlay network. IPsec VTIs, in essence, really simplify the configuration of IPsec for the protection of our remote links, to support things like multicast, and to simplify the network management and load balancing piece as well. Now, there are some restrictions for an IPsec virtual tunnel interface. You have to use an IPsec Transform Set. The IPsec Transform Set has to be configured in tunnel mode only. You have to use the Ike Security Association. And the security association, the Ike Security Association, is going to be bound to the VTI. Because the Ike SA is bound to the VTI, the same Ike SA cannot also be used for a crypto map. You wouldn't typically do that anyway, but it's just a point. For the traffic selectors, our static VTIs support only a single IPsec SA that gets attached to the VTI interface. That traffic selector for that IPsec SA is always going to be an any-to-any type of designation. Now, with our dynamic VTIs, we support point-to-point interfaces, but they only support a single IPsec SA as well. The difference is the dynamic VTI is flexible in that it can accept IPsec selectors that are proposed by whoever initiates the IPsec tunnel. All right. There are some other concepts that are important as well. For example, QoS traffic shaping, that's always going to be process switched. IPsec stateful failover is not supported with IPsec VTIs. The shared keyword, as far as tunnel protection goes, the shared keyword isn't really required, and it doesn't have to be configured if we specify the tunnel mode as IPsec IPv4. All right, we'll see that as we start to get into the configuration here. Now, the IPsec itself, if I was to compare this to, say, a GRE tunnel, for example, an IPsec VTI is limited to unicast and multicast traffic only. A GRE, of course, can support multiple applications for IPsec implementation. If a VRF-aware configuration is applied, whether we're using static or dynamic VTIs, DVTIs, a VRF cannot be configured in the Internet Security Association and Key Management Protocol profile, the Icmp profile. Instead, that VRF must be configured on the tunnel interface for our static VTIs. And then if we're using dynamic VTIs, we need to apply the VRF to the virtual template with the IPVRF forwarding command that we talked about in one of our previous lessons. All right, so it says here to start off the paragraph, the use of VTIs simplifies the configuration process when you have to provide protection for a site-to-site VPN tunnel. So the biggest benefit of a VTI is that we don't require static mapping of IPsec sessions to a particular physical interface. And this will become more understood as we start to look at the configuration, especially if you're familiar with what traditional IPsec VPNs would look like. Right? We don't have cryptographic map-based configurations. It's a very intuitive configuration, very, very simple. All right. The use of an IPsec VTI simplifies the configuration process when you need to provide protection for remote access or provide similar kind of simpler alternative protections to using things like GRE or L2TP. All right. And in this configuration, that IPsec tunnel endpoint actually gets associated with an actual virtual interface. Because we have a routable interface at the tunnel endpoint, we have a lot of the common capabilities that we would typically see with routing that can now be applied to our IPsec tunnel, right? So this IPsec VTI allows for the flexibility of sending and receiving both unicast and multicast encrypted traffic on any physical interface where we might, and that we would see that in an example of where we have like multiple paths between destinations and so on. The traffic is encrypted and decrypted when it's forwarded to or from those tunnel interfaces, and it's managed by the IP routing table. Using that IP routing to forward the traffic to the tunnel interface really simplifies the IPsec VPN configuration compared to some of our more complex processes of using things like access control lists with a crypto map in our standard IPsec configuration, if you will. All right. Now, a dynamic VTI really functions like any other real interface. So you can apply things like quality of service policies, firewall features, other security services to that interface. Without this configuration, we would have to use traditional IPsec configurations, and we would be limited to what IPsec is capable of. All right, so what are the general benefits of using a VTI? IPsec VTIs really allow you to configure this virtual interface, and then you can simply apply features to that interface. Features for things like clear text packets get configured on the VTI. Features for encrypted packets can be applied on a physical interface. But when the IPsec VTI is used, you can separate the application of the features, like things like NAT, ACLs, QoS, and you can apply them to either the clear text traffic or the encrypted traffic, or you could apply them to both if you wanted to. All right? So if we were using, say, for example, crypto maps, there really is no simple way to apply encryption features to that IPsec tunnel. And there are two types of VTI interfaces. We have static VTI interfaces and we have dynamic VTI interfaces. A static VTI interface configuration is typically used for something like a site-to-site connectivity, where the tunnel provides kind of this always-on access between two different locations. There is a benefit to using these SVTIs even over a traditional crypto map, because the users can enable dynamic routing protocols over the tunnel interface without the extra 4 bytes that would be required if you were going to add GRE, for example. It's not a significant amount of savings, but it could be pretty impactful in a large enterprise environment. We can also add additional features that can be directly configured onto the tunnel interface and onto that physical egress interface of the tunnel interface as well. All right, native IPsec tunneling is supported, and so on. A dynamic virtual tunnel interface gives us a secure and scalable connection option for things like remote access VPNs. It replaces the dynamic crypto maps and the dynamic hub and spoke methods that are used to establish tunnels traditionally. So we can use this for both server and remote configurations. The tunnels are going to provide an on-demand separate virtual access interface for every single VPN session. So the configuration of this virtual access interface gets actually cloned from a template that we configure, which includes things like the IPsec configuration, all the features that are configured on the virtual template interface, things like QoS, NetFlow, ACLs, and so on. A dynamic VTI really does function just like any other type of real interface. So just like we saw with our static VTIs, we can apply things like QoS, firewall features, and other security services as soon as that tunnel becomes active. The QoS features can be used to improve network performance for different applications across the network, and we can do things for voice, video, data, etc. All right. So when you use the VTI approach, we configure this virtual tunnel interface and we apply the IPsec profile in tunnel protection mode. It requires fewer configurations, and we're going to see this as we go through the discovery and we start to to look at the configuration in the discovery. All right, so we have, it says here that this tunnel interface behaves intuitively like any other interface. And we already saw the implementation of tunnel interfaces for GRE. This particular tunnel is, obviously the description identifies it as a tunnel to the branch office. We're using IPsec or AH, depending on how our IPsec profile is set up. We don't see that in this particular configuration. All right, the tunnel source is gig 00. We're taking the address from gig 00 to act as the address of the tunnel interface. The tunnel destination is the tunnel destination. So very similar to what we would see with the GRE tunnel. The only difference here now is that we're applying an IPsec profile to this configuration. All right. It says here IPsec VTI is another mechanism that's used to support VPNs. It is a routable interface, right? We talked about that already many times. It supports native IPsec tunneling and provides us the ability to create this tunnel interface. All right, so what are the benefits? Let's see, VTI features include the following. They behave like regular tunnels, one for each remote site of the VPN. Their encapsulation must either be IPsec, ESP, or AH, which is pretty typical for any VPN application. And their line protocol is going to depend on the state of the security association itself. Now we do see a configuration here, and again, we're not seeing the entire configuration, but the configuration is relatively straightforward if you look at it. And again, we'll do this in the discovery, but there are a couple of different things to keep in mind, right? For example, the dynamic virtual tunnel interface lifecycle. IPsec provides a profile that defines the policy for our dynamic VTIs. This is obviously going to apply to our dynamic VTIs, but the dynamic interface gets created, and then we identify Ike phase 1 or Ike phase 1.5, and the interface gets deleted when the IPsec session, say that 3 times fast, gets closed. All right. Now we can route over that tunnel or that virtual interface. We can do our traffic encryption and decryption and so on. Now the general steps to configuring a VTI interface, or VTI I should say, is relatively straightforward. You're going to go into your global configuration mode. You're going to create a profile where you're going to set your transform set. That's the part that we don't see in this configuration. You're going to go into an interface. You're going to give it an IP address. You're going to specify the tunnel mode. You're going to specify the tunnel source and the tunnel destination. Now, the profile itself, which we see referenced here as my profile, that's going to define the IPsec parameters that are used for the IPsec encryption between the 2 different endpoints. All right, the transform set, which is part of that profile configuration, specifies which transform set is used for the crypto map entry. All right, the interface allows us to specify the interface where the tunnel will be configured. In this case, it's just simply tunnel 0. IP address, we could specify an IP address directly on the tunnel interface. In this particular case, we're borrowing the IP address from the gig 00 interface. And then we define the tunnel, the mode for the tunnel. Tunnel mode IPsec IPv4. Now when we go through the discovery, I'll do context-sensitive help and I'll describe some of the other options that we might have here. We specify the tunnel source. In this case, the tunnel source is our gig 00 interface. We identify the address of the tunnel destination, which is 192.168.2.2. And then we associate the tunnel interface with our IPsec profile by using the profile. All right. Now, this is specifically a static IPsec virtual tunnel interface configuration. It would be slightly different if we were doing a dynamic configuration. In fact, really the only difference would be, instead of saying interface tunnel, I would say interface virtual template. And then I would specify the virtual template profile. I would also have to do a Icmp profile and a virtual template number to create the virtual template. I'm not sure that we're going to get into that. I'm sure that what we're going to be doing in our discovery is a static tunnel with IPsec, which is a relatively straightforward configuration. All right. What are some of the benefits? It simplifies our configurations. We can use these virtual tunnels to configure our IPsec policies, simplifies the VPN configuration, lots of interface support. We can identify features that either run on the physical interface or the VTI itself, whether it's clear text or ciphertext. We can support multicast. We can support scalability. It is a routable interface, so routing protocols can run over it. All right. Now there is I mentioned the limitations previously. We'll just kind of reiterate these. Only one IP unicast or multicast is limited to IP unicast and multicast, unlike GRE, and the iOS IPsec stateful failover is not supported. I also mentioned some of the other limitations as well. All right. We talked about, should I use a static or dynamic tunnel? We use dynamic tunnels for the hub if we're doing a large hub and spoke environment. Otherwise, we would use our static tunnels. And should I use static or dynamic routing? Again, that's going to depend on the complexity of your design, right? If you want to have a large network with lots of different endpoints and you want to be able to discover the network layer reachability information with all these different endpoints, most likely you're going to want to implement some sort of dynamic protocol. All right. Consider the following guidelines when deploying VTI-based site-to-site IPsec VPNs. Use the VTI-based site-to-site VPN as the default for individual point-to-point VPN links and for hub and spokes. Consider using Dmvpn or group encrypted transport for large environments that have either a partial or a fully meshed VPN. Okay? So again, we'll see the configuration of these VTIs later on. We're going to kind of go through a summary here. I'm going to kind of point out some of the configuration elements. I'm not going to read all this to you guys, but this will give you at least the steps that I was basically describing previously. So the first task is you need to set up your Icmp policies, basically, your Ike Security Association parameters, right? What are we doing for peer authentication? What type of encryption are we running? What type of hashing algorithm are we running? What Diffie-Hellman key exchange process or group are we going to use for the peering relationship? And I'll talk more about that in detail as we get into the discovery, because you do have to choose an appropriate Diffie-Hellman group based on the level of encryption that you're trying to apply to the IPsec tunnel. How are we going to define the lifetime? Is it going to be a data lifetime? Is it going to be a time lifetime? All right. It also requires you to create a pre-shared key to bind that to the VPN peer. That would depend whether or not you're using pre-shared authentication for mutual authentication, right? Notice here it says, how do I want to authenticate my peer? Am I going to use pre-shared keys? Am I going to use the Rivas, Shamir, and Edelman or RSA encrypted nonces or digital signatures to authenticate the peers? This is a kind of a shared a symmetric encryption process or authentication process. This is more of an asymmetric authentication process, but it does require the use of digital certificates, which means that you're going to have a little bit more complexity in the configuration. All right. What is our session protection policy? What are the encryption algorithms that we're going to use? Typically, that's going to be AES, right? What is the hashing algorithm that we're going to use? That's typically going to be SHA, but it could be a variant of SHA, maybe SHA-2, SHA-1 or SHA-2, and the different subvariants of SHA-2, right? What is the strength of the session key and exchange method? Again, we talked about the Diffie-Hellman key exchange process. I didn't get into it in detail, but again, it's very important that you select a Diffie-Hellman algorithm that's going to allow you enough key space to exchange the appropriate key based on the encryption or the encryption method that you're using. All right, and the lifetime for the users. So what we've done here is we can see kind of we've got different policies that are set up. These are some kind of the default policies, if you will. AES encryption with SHA using Diffie-Hellman Group 5. AES encryption with MD5 using Diffie-Hellman Group 5. Triple DES and is kind of legacy. We want to use avoid MD5, avoid anything that uses Diffie-Hellman Group 2, and so on. All right, but these are some of the default policies, and you can of course create your own policies as you need, because you might decide that you want to use AES with a different level of AES encryption, or you might want to use SHA at a different level. So you can create your own policies. There are specifically defaulted policies that are configured by default, and 65.508, 65.510, 512, 514. But we'll see what the configuration looks like when we're creating our own policies in our discovery a little bit later on. Obviously, you want to kind of avoid those legacy protocols. All right, 65.508 has the highest preference. Remember, the priority is the lower number is more preferred. So if I was to just allow the VTI configuration to choose one of the default policies, 65.508 would be used. There are some other Diffie-Hellman groups, 14, 15, 16, and so on, which provide even larger key space and stronger key exchanges, but probably not necessary. I think 5 is probably sufficient. All right. So we need to make a decision. What is the policy that we're going to use? And there's some best practice standards, some default standards that we might use based on what's pretty much considered to be standard industry practice today. All right, and certainly our discovery will take a look and take advantage of implementing that standard practice. The default lifetimes, as it mentions here, very conservative. If you don't agree on a lifetime, during the negotiation, change the lifetime to an acceptable value. We don't have to match the lifetime setting. We do have to match the encryption options. We have to match the hashing algorithm and the Diffie-Hellman group and so on, but we don't necessarily have to match the lifetime options. So we're going to run through a scenario real quickly. Site 1, this is the private network that's being protected, a passenger protocol, if you will. Site 2, 10.2.2, 10.1.1. These are the public peering addresses that we're going to use, 172.17.1.1, 172.17.2.24, and that's where the peering is going to take place. Looks like we're going to do pre-shared key authentication. We're going to use SHA-1 HMAC for our hashing algorithm, AES-128 for our encryption, Diffie-Hellman Group 14, which is pretty typical when you're using AES-128, and we're going to specify a 1-hour lifetime, which is pretty short, but that's what we're using in this particular case. So if you look at the configuration example, we're creating policy number 10. Again, the lower the number, the more preferred the policy. The authentication is pre-shared. Hashing is SHA. Encryption is AES-128. Diffie-Hellman Group is 14. The lifetime is 3,600 seconds, which is 1 hour. Not 1 hour. What did they say? They wanted a 1 hour lifetime. Yeah, 3,600 seconds. Yeah. Yeah, this is in seconds, not minutes. So 3,600 seconds is 1 hour. And then this is the actual pre-shared key for the peer. So this is referencing 172.17.2.24. That would be the configuration on router 1. All right. The password, the key is typed in plain text, but so you certainly want to make sure that you use a relatively strong key. Router 2's configuration is essentially identical. The only difference is, and by the way, the policy numbers do not have to match on the routers, but the address obviously would be reversed in this particular case. All right, and then they kind of break down each of the commands here, but I think the commands are pretty self-explanatory. All right, now how do we verify that the peering is working? Show Crypto Icmp SA is a way for us to verify that that phase 1 process is completed. We can look at our policy, of course, make sure that we have a policy that's going to match our peer, but show crypto Icmp SA is something that we can use to identify whether or not the peer is functional. Now, this does not mean that we're doing encryption. We would use the show crypto IPsec SA command to verify the encryption status or phase 2 status of the tunnel itself. All right. So many different, and there's some other troubleshooting commands that we can use as well to verify the overall function. And when we go into our discovery, I'm going to spend more time, but certainly we want to make sure that we were able to negotiate the session first. If we were, then we can start to verify and troubleshoot the phase 2. And then if phase 2 is working, if I do a show crypto IPsec SA and I see encrypted and decrypted packets and I see my my SPIs created, my security parameter indexes created, then maybe I need to start troubleshooting routing. And if routing's working, then traffic should be flowing through the tunnel. All right. So show crypto Icmp policy just gives me information about how my policy was configured. We can also use the no crypto Icmp default policy command to disable those default policies, which means that we would have to statically configure a policy as well. Also those wouldn't show up in the output. Show crypto Icmp SA. The session will be established only after IPsec requests it. In other words, only after interesting traffic is generated here. Now, we'll probably see this in the discovery as well, but I want to make mention of the different states that you might see in this particular case. Now, we see here the state is QM idle, and actually when you type in the show crypto Icmp SA command, the state should always be QM idle. QM stands for quick mode. If the state is key EXCH, for example, that means that the pre-shared key is not configured correctly. You could also see some other ones as well. But QM idle basically means that the tunnel is up and the Ike SA key exchange was successful, but it's idle. It remains authenticated in what we call a QM state or a quiescent state, but it is active. All right. Like I said, you could see some other options here. I mean, you could see some other outputs here as well. If you see, for example, no state, the Icmp SA process was started, but it hasn't continued to form the SA because there's a connectivity issue with the peer. You might see SA setup. Both peers are basically agreeing on the Icmp SA parameters, and they're going to move along the process to establish the rest of the association. Like I said, key exchange or key EXCH, both peers have exchanged their Diffie-Hellman keys. They're generating their secret keys, but it could also stay in the state, meaning that you have a mismatch authentication type or a mismatched pre-shared key, and then you wouldn't move on to the next phase. And then if you did happen to move on, you might get into the key auth stage, where this is authentication in main mode and then you're gonna basically the Icmp SAs were authenticated in main mode, and then they're gonna proceed to that QM idle from that point forward. All right, but this is really what you want to see. You want to see QM idle. That means that the Icmp SA is idle and authenticated, and so on. And there's some other outputs. You can do a show crypto session. A lot of these we'll look at in the discovery. You can do a show crypto IPsec SA to verify really the last phase of the establishment, and so on. And we'll talk more about some of the other things that we would look for based on that. But again, we always want to try to identify the functionality of phase 1 first before we start to troubleshoot and identify issues that might exist with phase 2. And that's what that flow chart was representing. This is phase 1, this is phase 2, this is basic routing over the tunnel. All right? So which command would be used to verify the status of an Ike peering SAs? Show crypto Icmp SA, as we can see from above. All right, now we can look at our policy, but it doesn't show the active status. All right, so that's very important. Show crypto. I don't know why I selected that one. There's no IP. It's just show crypto. All right, there's no option to use IP in the syntax. So we're going to wrap up this lesson. We're going to get into our discovery, where we're going to go through and configure some VTIs and do some more troubleshooting and verification and so on. And then we're going to wrap up this module. All right, everybody, let's go ahead and get into our next discovery, discovery number 17. We're going to configure a static VTI point-to-point tunnel. So we're going to implement this static VTI point-to-point tunnel. We're actually going to configure this on router 2 to establish a VTI point-to-point tunnel with router 3 in their topology. This is going to allow the hosts at the router 2 site and the hosts at the router 3 site to securely exchange data across this kind of simulated internet connection that we have here. Hosts on each of the networks should be able to access the resources on the other network just as though they're directly connected to each other via some sort of private network. Obviously, in this particular case, we're trying to benefit from the functionality, the security, and also from the overall management policies of our overall private network. Router 3 is already pre-configured to support this exercise, so we're going to be focusing our attention on configuring the static VTI point-to-point tunnel on router 2 and then verifying that VTI point-to-point tunnel operation on router 2 as well. All right, we're going to be using commands like authentication pre-share, clear crypto SA counters. We're going to be looking at a crypto IPsec profile, setting up a transform set, specifying the pre-shared key peer authentication information, and then setting up our Ike proposal, which includes our encryption mechanism, our Diffie-Hellman group, our hashing algorithm. We'll also take a look at setting up the tunnel interface and going into tunnel interface configuration mode, configuring those elements as well, and some other tasks throughout this exercise. So our first task overall is to go ahead and configure the static VTI point-to-point tunnel. We're going to implement a static tunnel on router 2 so that we can establish that point-to-point tunnel with router 3. Again, router 3 has already been configured. Now we could cheat if we wanted to and simply kind of take that configuration from router 3 and then basically duplicate it on router 2 with a couple of minor changes to the configuration. But I'd like to go ahead and talk about the individual steps that we would go through on router number 2 as if we're establishing this configuration from the very beginning without any kind of pre-configuration or kind of preconceived configuration that we already have on router 3. So we're not going to actually, normally I would go through and investigate what we have on the other router, and that would certainly save us a lot of time. We could even cut and paste some of these configurations, but I want to make sure that we're doing this kind of step by step. So in our configuration, let me go ahead and pull up router 2 real quick. And in our configuration, we got an extra tab here. Let me go ahead and close that. Router 2, we're just going to do a quick show IP interface brief, just to show that we don't have a tunnel interface configured here. We've got kind of an inside and outside LAN interface and a WAN interface. Keep in mind 172.17. That's generally that's our public side, and then the 10.10 is our private side. All right, so we're going to go ahead and set up our Ike policy. This is our internet key exchange policy that we talked about in the lecture here. We're going to use a crypto Icmp. If you recall, Icmp is kind of equivalent in Cisco speak to Ike or internet key exchange policy. We're going to go ahead and set up policy number 10. Now we need to specify things like authentication, what is the encryption method that we're going to use, what is the Diffie-Hellman group that we're going to use, what is the hashing algorithm that we're going to use, and what is the lifetime. Now, some of these will default out. The lifetime, for example, would default out, and we don't necessarily have to establish what the lifetime is. The default is 86,400 seconds, but we're going to go ahead and configure this because we want to make sure that we have a policy that matches our peer router. Doesn't have to be the same policy number, right? But it does have to have the same policy parameters. So we're going to do pre-shared authentication. We're not going to use RSA or DSA authentication. Just so you can see, we have those options. We can do RSA signature or RSA encryption. Both of them, the Rivas, Shamir, and Edelman, those are the three gentlemen that came up with this encryption technique. We're going to focus on pre-shared keys because those are relatively easy to implement. As far as hashing algorithms go, we can see we have several different options. MD5 or message digest, SHA, and then the SHA standard 2 options, which are 256 bits, 384 bits, and 512 bits. We're going to go ahead and stick with SHA. It's still relatively secure. It offers 160 bits of encryption, so that's still relatively secure. Then we're going to say our encryption, and again, we have several different options here, triple DES, AES. Even within the AES standard, we have the three different options, 128 bits, 192 bits, or 256 bits. Clearly, we're not going to use DES, the data encryption standard, using only a 56-bit key. Obviously not going to be secure. We're going to go ahead and stick with AES 128. And for that reason, we're going to run Diffie-Hellman Group 14 at least, because we need at least a 2048-bit key space to be able to exchange the keys appropriately. All right. Each of these Diffie-Hellman groups are kind of paired with different encryption techniques. Diffie-Hellman Group 14 is typically used with AES 128. And we're going to go ahead and set a lifetime of 3,600 seconds. Now, normally what I would do is I'd want to go into router 3 or the peer router, and I would definitely want to check the crypto configuration. Spell that right, crypto. Let's just do Icmp because I don't want to pull out the other crypto stuff. And we can see that we have essentially the same thing, AES 128, pre-shared key authentication, Diffie-Hellman Group 14, lifetime of 3,600 seconds. Now notice that the hashing algorithm is not specified here. If we go back to router 2 and we put that command in here, let's put a do there, we can see the same output here. That tells me that the hashing algorithm of SHA is the default. Also, because encryption AES 128 is not there, that tells me that the default encryption is AES 1, or the default AES encryption is 128. So we have a lifetime of 1 hour. We have our key exchange method of Diffie-Hellman Group 14. Our hashing algorithm is SHA. Our encryption algorithm is AES 128. And our authentication method is pre-shared. Okay. Now our next step is to go ahead and establish our pre-shared key with the peering router. Peering router is going to be router 3. The address is 172.18.4.2. So I'm going to say crypto. And again, this is something I could kind of duplicate between the routers. Obviously, the IP addresses would be different. But if I wanted to copy this just to make sure that it's accurate, I could do that. Now, obviously, we don't want to use a key of Cisco. We would probably want to use something a little bit more secure, but this is for demonstration purposes. Again, if we go to router 3, we can see that we have the same output here, right? Crypto, Icmp key, Cisco, and then the peer address, which is 172.17.1.2. And if I go back to my show IP interface brief output, I can see that that's the address of this particular device. So that's accurate. All right, so that's step number 1. Step number 1, basically, or 1 and 2, I guess I should say, that takes care of our phase 1 configuration, meaning how do we, what kind of key negotiation are we using? How are we authenticating the peer? What are we using for encryption, lifetime, etc. for phase 1. We specified our pre-shared key, which is our authentication. Now we need to define the transform set. If you recall from our discussion in the lecture portion, the transform set really determines the encryption and the data authentication hash for the IPsec SA, or the IPsec Security Association, which is phase 2, by the way. The transform sets do have to match. We have to have at least one equal policy between the peers. We can have multiple policies defined, and we can negotiate a particular policy, but the transform set does have to match, or at least we have to have at least one policy that's going to match between the peers. Now, we are going to create our IPsec Transform Set. This is going to be for the user traffic protection. We're going to use ESP, Encapsulated Security Payload. We'll go ahead and set up 128-bit AES encryption. And then we're going to use SHA-1 HMAC as our authentication transform in this particular case. So crypto, IPsec, transform set, and we'll just call it my set. And we're going to say ESP AES 128, and we're going to say ESP SHA HMAC for the hashing variant. Okay? All right. So if I come over to router 3, I want to see that I have a similar transform set. Show run pipe section my set. Now keep in mind, we don't. Let me try IPsec here. We don't necessarily have to have. It doesn't have to have the same name, but it does have to have the same parameters, right? So just because I call it my set on one router doesn't mean I need to call it my set on the other router. But we can see that we have our AES. Again, the 128 would be the default, and SHA HMAC here. All right. Which brings us now to the 4th step, which is to create our profile, what we call our IPsec profile. This is going to bundle the transform set to the profile, or join that transform set to the profile. And then you'll see later on that we'll apply that to our interface. So crypto IPsec profile, let's just call it my profile in this case. And I'm going to go ahead and say set the transform to my set. Make sure that you do reference the transform set that you created as a case-sensitive name, obviously spelled correctly. All right. So now the only thing left really is to go ahead and create our tunnel interface on router 2. Now just go back to router 3. We can see that we have a profile here as well. Crypto IPsec profile, my profile, set transform set, my set. So again, most of these configurations are duplicated on each router, and that is certainly my recommendation. If you're going to go through this configuration, it's probably best just to go ahead and type it in Notepad, cut and paste, because you don't want to have any typos or anything like that. So let's go ahead and go into interface tunnel 0. And we're going to say IP unnumbered. We're going to go ahead and take the address from, why is it not doing it? IP unnumbered, there we go. Ethernet 10. And our tunnel source is going to be Ethernet 10. If I do a show IP interface brief, and I include 10, we can see that that is our public interface, right? 172.17, that's the public side. Our tunnel destination in this case is going to be the other router. And again, this is something that you would want to be reachable. So in fact, you might even do a quick ping to make sure that that particular destination is reachable. Notice that the tunnel interface changed to up, even though we haven't generated any interesting traffic. We actually don't have any routing over the tunnel. We haven't actually configured anything to go over the tunnel. We haven't even actually applied the IPsec profile to the tunnel. But again, because the state of the egress interface is up, the tunnel interface is going to have a line status of up as well. All right, our next step is we need to specify what type of tunnel encapsulation we're going to use on this interface. Plus, we're going to go ahead and apply the traffic protection policy by referencing that IPsec profile that we configured previously. So I'm going to go ahead and say tunnel mode IPsec, and we're going to do this in IPv4 because we're carrying the traffic over IPv4. And the tunnel goes down because we haven't specified the protection IPsec profile of my profile on the interface. So it's saying, oh, you've established that you want to run IPsec, but we don't have any profile or any kind of IPsec configuration tied to this interface. So for that reason, we're not going to be able to bring the interface up. But you'll notice as soon as I applied the profile to the interface, Icmp started to negotiate the tunnel, and then the tunnel came up. All right. Our next step is to do some sort of routing. In this case, we're just going to basically do static routing. The 2.0 subnet is the other private LAN, and we're just going to send that over to tunnel 0. All right. Now we could run a dynamic protocol over this tunnel, but we would have to add some GRE on top of that as well if we wanted to be able to use multicast or broadcast traffic because of the fact that this is an IPsec tunnel and doesn't have GRE. All right. So really everything is configured at this point. Our next task, major task, would be to go ahead and run through some verification steps, right? We want to verify this static point-to-point tunnel. So we can start with phase 1, or we could simply go to phase 2 and verify the status of the IPsec SA. All right. So for example, if I come in here and do a show crypto IPsec SA, there's a couple of things that I'm looking for here. All right. There's also going to be a couple of things that are missing from here, but we do want to see some of the basics here. We want to see that we have basically what we expect to see with regard to the local address of the tunnel. We want to see things like encap and decap and encrypt and decrypt. Now we don't see that in this particular case because we actually haven't generated any traffic across the tunnel. But as we start to generate traffic across the tunnel, we should start to see these numbers increment. We can see the local endpoint, we can see the remote endpoint. We definitely want to see an SPI, Security Parameter Index. This indicates that the tunnel actually was established, and you're also going to see an inbound SPI and an outbound SPI. That's very important as well. That establishes that the tunnel actually has come up and is operational in this particular case. We see the status of active listed here. So that's something that we definitely want to look for. All right. Now we could also come in here and do a very basic check, a show interface tunnel 0, for example, to see that the tunnel is in the up state. It should be in the up state. We can see that right here. Tunnel is up, line protocol is up. All right. Of course, we can see some other characteristics here that are kind of important. What is the tunnel MTU? What is the tunnel source? Tunnel destination. These are important concepts that we need to take a look at as well. All right. Now, we can also verify our routing table. If I do a show IP route, I certainly should see the 10.10.20 subnet listed. And the next hop is there, the exit interface is the tunnel interface. Now, if the tunnel interface were down, this route would not show up. All right. So let's go ahead and generate some traffic. I'm going to just generate some traffic to the 2.1 interface, which is the inside or LAN private interface for the other router. And I'm going to source this traffic from my LAN interface. All right, so I can see that the ping went through successfully. Now if I go back and do my show crypto IPsec SA, I should see some packets encapsulated, packets encrypted. packets decapsulated, packets decrypted, and so on. All right, so that tells me that traffic is from those subnets is passing over the tunnel. All right, just by doing a basic check. Now, if I really want to check, I can come into PC1, show IP interface brief. This guy is 10.10.1.11. I'm just going to do a ping to 10.10.2.12, which is the other router on the other side of our private network. All right, so the ping's not going through. Let me go to PC number 2 and do a quick show IP interface brief. That is up and operational. Show run include gateway. We know that we have reachability. Let me check my physical layer because I might have messed up the cabling here. Ethernet 1.0 to Ethernet 1.1. We already know these links are correct. So I'm curious why I cannot ping. I can ping there. Let me try to ping my gateway from PC1. I can ping my gateway there, but how come I cannot ping PC2? 10.10.2.12, Ethernet 1.0. All right. Let's see. Looking at the diagram here, R3. We know that there's routing between R2 and R3 because the tunnel came up. But let me check the route on R3 and see if we have a static route, show IP route on R3 to the 10.10.1 subnet. We do. Ping 10.10.1.1, source Ethernet 1.0. So we have reachability there. This is very interesting. I'm not sure why. Let me check the other side. Ethernet 1.0 to Ethernet 1.1. This is very strange because we do have connectivity. Let me try this. Ping 10.10.2.1. So the only other thing I could think of is that this router doesn't, or this PC, which is a router acting as a PC, show run include gateway 10.10.1.1. Interesting. Let me try one more thing here. Interface Ethernet 1.0. Let's shut that down and do the same thing here. Shut that down. And bring those interfaces back up. And see if that helps the issue here. We know that the tunnel is working. And the reason we know the tunnel is working is because I can source the traffic. If I do a show IP interface brief and I do a ping to 10.10.2.1 source 10.10.1.1, the ping goes through and we're getting the endcaps and the decaps. So I'm not sure why in this particular case these guys are not able to ping. Oops, ping 10.10.1.1, 10.10.2.1, 10.10.1.1. Very interesting. Debug IP Icmp. Let me see if it's getting to router 2. Debug IP Icmp. So for some reason, the traffic is not getting out of the PC over to R3 Ethernet 1.1. .1.2.1, that's correct. And the tunnel interface should be 172.18.4.2 because it's taking the address from Ethernet 1.1. And the tunnel interface here, 172.17.1.2, which is correct. And the middle router shouldn't matter in this case because the data is being encapsulated. Let me do this. Let me do a Wireshark capture on this link. Now we won't see the payload information because it should be encrypted, but I should at least see the packets being generated when I do the ping from PC1 over to PC2 coming across the link. I won't see the payload because again it will be encrypted. I'm reticent to say that it's a GNS3 issue, but the tunnel interface definitely appears to be operational. I mean, I know it's operational. So let's do a ping 10.10.2.12. And do we see that information going across the interface? We do not. We do not see it. So let me try this. Let me stop the capture here. It's going to let me stop the capture. There we go. And let me start the capture here. All right, let's try that ping again. Yeah, for some reason, it doesn't appear. Let me try one more spot here. It doesn't appear that the traffic is being routed despite the static route. If I do the capture here, see if I see the pings being generated by the PC. The only other thing I could try is to delete the links between the routers and kind of re-add them. Maybe there is something going on with GNS3, but let's do this ping one more time. We should definitely see the pings here because we have a gateway. All right, so we are seeing the pings here. No response seen. And the source address is 10.10.1.11. Destination address is 10.10.2.12. It's very interesting because we're not getting like an Icmp unreachable message when the ping goes through on router 2. Now if I come over to router 2, show IP route, the 10.10.2.0 subnet directly connected to tunnel 0. So I'm not sure why actually that's not being encapsulated. It certainly should. I mean, the traffic is routed to the right destination. We have a static route that points to the tunnel interface. The tunnel interface is operational, but for some reason the traffic is not being encapsulated. So I'm going to go ahead and delete this link. And I'm going to delete this link as well. I'm just going to kind of go through here and add all of my physical layer back. Something definitely strange going on here. All right, so this is Ethernet 1.0, and that's plugged into Ethernet 1.1. This is Ethernet 1.0, plugged into Ethernet 1.0. Ethernet 1.1, plugged into Ethernet 1.0. And then Ethernet 1.1 plugged into Ethernet 1.0. All right, let's go back here. Our routes should be there. Do our ping again. Certainly, if you walk through the process, we know the traffic is leaving this router, this PC. If I do a show run, include gateway, the traffic is being sent to the traffic is being sent to 10.10.1.1. Show IP interface brief, 10.10.1.1 is here. The interface is operational. It is the appropriate interface, 1.1. And this router has a static route for the 10.2 network, 10.10.2 network. And again, if I ping 10.10.2.12, let's try this. Ping the client from the router side, source 10.10.1.1. I believe that's going to fail as well. But if I ping the LAN side, and if I ping 2.1 source 10.10.1.1, that ping goes through successfully. So I'm not sure what's happening here. There's definitely something strange going on, but the configuration is correct. There's definitely nothing wrong with the configuration. If I do a show crypto Icmp SA, we can see we're QM idle, right, for the connections. 1.2 to 4.2 and 4.2 to 1.2. And if I do show crypto IPsec SA, I can definitely see NCAPs and DCAPs. I can see my inbound and outbound SPIs, my transform sets. There's 2 SPIs outbound, 2 SPIs inbound. That makes sense based on the traffic that's being generated. So I'm not sure what's happening here in this particular case. But I'm definitely going to, I don't generally like to do this, but in this particular case, I am going to say this. There's definitely something going on with GNS3 that's causing this to fail for some reason. Because we know the tunnel's active, we know the tunnel's passing the information it should be passing based on what we did the testing from the local LAN side route, the router LAN interfaces. We know that the traffic is definitely being passed over the tunnel. So we're going to go ahead and assume in this particular case that it is a issue with GNS3 in this particular case. All right. In any event, as we do the different verifications, had those pings worked from PC1 to PC2, it's going to bother the heck out of me forever, but had those pings worked from PC1 to PC2, we would have seen in the show crypto IPsec SA additional NCAPs and DCAPs as well as encrypt and decrypts for the traffic passing back and forth. Very, very strange, but you know, I'll probably do a little bit of an investigation after this, maybe restart the project and see if it fixes itself based on that. But in any event, that is this discovery, very basic discovery. Just to reiterate some of the tasks and some of the configuration pieces that we did, our first step was to go ahead and set up our show run section IPsec, was to go ahead and set up our show run pipe section Icmp, was to set up our Icmp profile, which we've done here. pre-shared key, encryption AES, authentication, lifetime, and then we specified our peer information. And then we did our transform, which was the next step, specifying the transform set. And then we set up our profile, show run, pipe, section, profile. And we specified our my profile, which was, by the way, also applied to the tunnel interface. And then we configured our tunnel interface. So we're taking the IP address from our outside interface, where that's the tunnel source as well. The tunnel mode, this is the tunnel destination. We know the tunnel is active. We know it's sending traffic because, again, I can do a ping to 10.10.2.1, source that from Ethernet 1.0, and it goes through just fine. All right. We're also seeing, based on the show crypto IPsec SA, we're seeing the encap and decap and encrypt and decrypt. There's the encaps and encrypt. And then, if of course, we should see show IP interface brief. Yep, this is 10. Oops, I'm sourcing it from the wrong interface. Let me source it from Ethernet 1.1. And I should see the encap and decap and encrypt and decrypt incrementing there. We can see that here. All right. So we know the traffic from each of the LAN sides is passing over that tunnel interface. Again, not sure what's going on here, but we're going to go ahead and table that discussion. And I'll take a look and see. And if I can figure it out and come up with a little addition, I will go ahead and update the video and you guys will learn what the issue was. Most likely I'm 99.999% sure it's going to be related to something that GNS3 is doing. All right, so we'll wrap this discovery up. We'll see you guys in our next lesson. We're going to wrap up this lesson by doing a module review and also the summary challenge for the end of this lesson. But then we're going to start to get into some wireless topics. All right, so we'll see you guys there. All right, so welcome back from the discovery. We're going to go ahead and wrap up this module by going through our summary challenge, which is just a few questions here. Which network topology is used when every network has a direct VPN connection to every other network? This topology provides any-to-any communication and provides the most optimal direct path. That would be a full mesh, right? Everybody connected to everybody would definitely be considered a full mesh topology. Which three statements is true about site-to-site VPNs? They authenticate VPN peers and network devices that provide VPN functionality for an entire site. They provide transmission security between sites over an untrusted network. That sounds about right. They eliminate the need for basic network traffic controls. No, we still have to be able to control how the traffic is switched and how it's routed. They often encounter problems with traffic filtering. They're supported only on Cisco routers. That's not true. They can be used as replacements for classic routed WANs. Absolutely. We talked about that. They eliminate the need for high availability. They eliminate the need for QoS. So I guess A in this case would be applied because we still want to have availability. We still want to be able to prioritize important traffic. They authenticate VPN peers and network devices that provide VPN functionality. Yeah, of course, we authenticate our endpoints that are participating in the VPN. All right. Which option is an encryption mode supported by IPsec? Tunnel mode, right? Not clear mode, bypass mode, pass-through mode. These are not defined modes. Tunnel mode or transport mode. Which VPN solution relies on IKEv2? That would be Flex VPN. We talked about that. It's not that you can't use IKEv2 with these other technologies, but Flex VPN requires it. Which two encapsulation methods are supported by Cisco IOS VTIs? We can do ESP or we can do AH, right? Because we're using traditional IPsec framework for the VTIs themselves. Which command can be used to verify that IPsec tunnels are established and to display the number of encrypted and decrypted packets? We didn't actually talk about that in the lecture. We looked at this in our discovery, but remember, we're actually looking at what is encrypted and decrypted. That's going to be our crypto IPsec SAs. Show Crypto IPsec Security Association detail. Remember that showed us our encrypted and decrypted packets and encapsulated and de-encapsulated packets. And we also saw the SPIs, the security parameter indices, in each direction for the VPN tunnel. All right. Which of the following is a stronger hashing algorithm that's used by Ike? A hashing process is either SHA or MD5. Diffie-Hellman is not a hashing process. It's a key exchange process. And the secure hashing algorithm, SHA-1 is a 160-bit hashing process, whereas MD5 is a 128-bit hashing algorithm. All right, so we'll go ahead and wrap up this module. We'll see you guys in our wireless section coming up next. See you there.